Good morning, everyone. Good afternoon for some of you. I'm Marcelo Pias. I work at Federal University of Rio Grande in southern Brazil. So it's extreme south. We are close to Uruguay. So that tells you how south we are in Brazil. I want to talk about some of the concepts around what is being called the Industry 5.0, and give some examples of how we are approaching with that concept, some of the applications we have, and also discussing some of the system level issues that we are having in that specific application. I want to first to bring this the ideas of generations that we have for the industry, or people have created this slots. I'm not sure if they if they're really real in the sense of timelines, but that's what people have been discussing. So we have the first generation where we have the mechanization of the industry, so steam power. The second generation where we look at the electricity enabling the mass production assembly line. Third generation where we have automation. So this is the sort of the supervisory systems that we put for the assembly lines. And the fourth generation, or the Industry 4.0, where now we integrate sensor or cyber physical systems and actuators, but not only that, we make them to communicate, to create this internet. So we call it Internet of Things or Industrial Internet, and also bring some intelligence for those machines. Okay, and then we have this new this new generation where we look at the personalization or customization of the process as being a driving force, and also looking at how we can better integrate people into the process. In the Industry 4.0, what we see is that we see this acceleration of the production process, so make efficiency as something that people really took as the major issue. And then we at the same time we brought lots of systems and technology, and automation is sort of priority in the agenda. And but then we see also the automation brings efficiency, but also it sort of changes the way or the roles of the people working in that in the kind of industry and environment. But this transformation is what we have been calling the Industry 4.0. So then this is of course this is a more European view of the industry, but the idea for the Industry 5.0 is that we bring back humans to the loop. So it's a human-centric, whereas in the Industry 4.0 we make efficiency, and then we take people from the loop so that the efficiency can be accomplished. But also in the Industry 5.0 we look at how we can make products and services, and then we respect the limits of the planet. Okay, so that's the sustainability as a driving force for the Industry 5.0, and resilience, how we can make the technology that is resilient and flexible and adaptable. In this whole space, there are enablers, some technology enablers, important technology enablers for the Industry 5.0. So one of the enablers is the idea of individualized technology, where we link humans with technology. So we have technologies like tracking technologies for mental and physical strains and stress of employees. Again, employees as at the top of the agenda here. So augmented reality and all those kind of interactions between people and the technology that you enable a new type of interaction, which is that now the machines interact with the humans, and that's supporting collaborative robots that can work with people, and also the concept of twinning. So twinning is now the sort of the virtual replica of the environment, and the environment is not only the machines. The environment, they have now people. So it's twinning the machines, interactive people, twinning people. And that's the concept of digital twinning. So that's kind of enablers for this Industry 5.0. And I wanted to talk about some of the projects that we went through. We are still progressing this particular project, okay? And then we are thinking about those Industry 5.0 concepts, and I'll try to bring some examples for us to look at the space. So this project that I'm going to explore is really a project that we're developing with one of the global leaders in car manufacturing. So it's a vehicle assembly line type of environment. Okay, and so we are exploring the twinning or the digital twin in this project as one of the enablers for the Industry 5.0. So what you have here, we have the virtual space, which is mimicking the real space. So we have data coming from one to another, and then we have information process on the other side. Okay, so this is the sort of a very broad view of the twinning concept, which really starts for for products. I think it's probably 20 years ago. Okay, but the idea is that the twins, they are connected to data and process, as we're seeing in this diagram. And the goal is to improve the performance of the physical entity through computational techniques applied on the virtual twin. And some of the technologies that's in this limit of Industry 4.0 and 5.0, embedded system, Internet of Things, and the cyber physical system. So the use of digital twins in the life cycle of automotive products is still little explored in Brazil, and that's the project that we are developing with one of this Japanese company. So the idea here is that we have a production cell of magnetic clutch rotors for air conditioning systems in our vehicles. Okay, so basically, pretty much, I would say the majority of the vehicles produced in Brazil, they use this this part that we're going to explore. So the idea is that it's a quality control process. It's very typical application for improving efficiency in this type of production line environment. And we want to provide real-time management and analytics through a platform, minimize cycle time of the production line. So this is the sort of a typical problem space that people would come searching for a solution. And of course, you can see here that there are many opportunities for intelligence, many opportunities for machine learning, and I want to talk about those opportunities. Okay, so this is the sort of the just a high-level overview. This is the sort of the part that we want now to look at and do some inspection of that specific part. Remember that that part is part of the air conditioning system of a passenger vehicle, car. So we have all the dimensions of the part. We have many features of this specific part, and so this are the sort of inspections that we want to do for quality control. So there are like 10 inspections. So some of these inspections they are visual. Some of these inspections you need to turn the rotor to see if there is any noise or but pretty much you have like a 10 pretty very well defined inspections that you want to make. Some of these inspections we do like once an hour. Some of these inspections we do all the time in the production line. Okay, I think I just show you a quick example just for you to have an idea. So there is an operator here, so there's someone, and so he's doing the sort of a manual inspection and following those those 10 type of inspections. So he's checking if there is any sort of noise. Now he's going to count. So he's checking the dimensions. If the dimensions are within boundaries, he's now going to count those features there, and and then he's going to complete the inspection. And this is done manually for all the parts in the production line. So so basically those are the steps that the user follow, the operator follow. Okay, so and of course now we have like 2 minutes or even sometimes 3 minutes that you need to do those inspections. So there is a sort of a 3 minutes that you need to wait for each part in the production line. And the idea here is that how we can automate this process and make it less than 3 minutes. Okay, so this is the sort of the problem that the company brought, and then the approach that we are taking is that we, of course, we could explore the space and maybe we could twin those process, and then we are making these twins of each of those process. So we group those inspection into 3 twins. So we have the dimension, the visual, and the vibration twins. So each of those we are monitoring assets, producing data, goes to the model, and the model provides feedback, assets, and that's the sort of cycle we follow for each of those twins. And of course, there are features that we need to be looking at. For instance, the vibration, the bearing noise. How we can, the operator would hear the noise you saw in the video, but now how we can use technology to mimic that kind of sense, human sense in some way. So far in Indus 4.0, everything is fine. And then we have now the various parts that we produce. So there is the sort of the physical integration. So we are now producing a sort of inspection, let's say, cage. And that inspection cage, we have all the sensors to do all the different types of inspections. So we have cameras to do the visual inspection. We have lasers to do the dimension inspection. So very precise laser going on the face of the part. We have now we have to integrate this cage with the robot manipulator. So so how we can do that? So we have an interesting issue, because now we have the different modules, and those modules, they are in different systems. There will be, in our case, they are in Raspberry Pi and in Jetson Nano and NVIDIA Jetson Nano, but you could imagine some of those could be in a sort of microcontroller or the Arduino based, as we've seen in many talks this week. But they also have the synchronization of the system. So we're using, in the first version, you use MQTT for it's a publishing subscribe system. But now we are moving to ROS, which is the robotic operating system. It's not an operating system; it's a middleware but it's called robotic operating system, so that we can synchronize the different twins of the system. And the vibration inspection of we are using mostly accelerometer, say, microphones, and then doing some fast Fourier transforms, and that's feeding some of the machine learning models we create. So this is all the sort of the Industry 4.0 type of solution, okay? But then we have the question, and that question is very strong for us now, is how can you keep the user in the loop? So if you wanted to do just an Industry 4.0, so that all those components that I just showed you would be okay, would be, you know, integration. Of course, there are some technical challenges, especially in the models. But I mean, the question is, you know, we are removing the operator, so we are bringing a system that is able to do 15 seconds cycle, to do all the 10, let's say, inspection in 15 seconds, not in 3 minutes or 2.7 minutes before. So fully automated inspection. Then the way we are bringing the user to the loop is that so the role of the user is changing, the role of the operator is changing, and we are giving the tool for the operator to do analysis or failure analysis of those parts which fail the test. So it's like doing a sort of debug mode, if you like, so that you put back the parts into the cage, for instance, and you press enter, and you go step by step to analyze each of the inspections or the automated inspections. Okay, so this is a sort of collaboration between the human and the robot. I'll show you a video now, but it's you know, it's changing the role, it's giving more power to the operator, and also it's taking the operator to the sort of analysis mode. So it's a sort of more high-level job, and you know, using more of the operator brains. That's how we are framing and how we are seeing this transition to 5.0. This, of course, this is just the beginning. There are many other things that we need to consider, but I just wanted to highlight that that's something important. Okay, so this is just to give you an idea of the type of integration. So we have the robot manipulator there. This is how the part is being, let's say, produced. We have like you know, the bearings being placed in the sort of shelf of the part. Okay, and then the robot is doing that, and the robot is going to take that part and is going to put in the inspection cage that we developed. There's integration between this inspection cage and the robot, of course, and then the failure analysis is where the user can interact and can use this, you know, what we're defining as debug mode, you know, going step by step, you know, is what I'm going to show in this video. Of course, this is a prototype that we're still building. The prototype, it's not fully integrated with the robot yet, but it's just to give it a flavor of where we are heading with this project, and the concepts that the user in the loop is important, and not remove the user is also important, which has been done extensively in the Industry 4.0 because of the efficiency and performance. So just click here. So this is the cage. As you can see, we have cameras, we we have you can see the laser point there, the red one. Of course, there are many things happening here. This is all controlled by the pub sub system. So the pub sub is doing steps by step. And here is the opportunity that the user can take all the parts that failed in the process and do this debug mode analysis in the cage. This is likely to happen not in the sort of hours that the machine is or the production cell is done, or maybe there is a sort of a replica of the cage that the user can do that kind of interaction. Okay, so but I wanted to explore more what is behind this system. Okay, this and I want to explore now, looking at the what is underneath what I just described. I want to explore the issue that we have been facing this project, okay, that we call the transition challenge. So the transition challenge is that our models, we have like now 3 machine learning models. They are trained on the cloud. So use Google Cloud for training, and then we have those models. So how we can take those models and put in the device, which are part of the inspection cage. Okay, this is what we call transition challenge, and then we do some analysis of the challenge of the issues around that. So I think 2 questions that we addressed is the performance and accuracy impact of taking those models and putting the sort of resource constrained devices, okay, so the edge devices, and also the power footprint. So running those machine learning model, we have 3 of those in a sort of edge device, but looking at mostly at performance watt metric. So it's really looking at the performance and power consumption at the same time. It's not only power consumption, and this is sort of more it's a more modern view of analyzing systems that we look at. So the transition challenge, it relates back to this slide that Marcelo Rovai yesterday presented. Okay, and then I want just to highlight in this slide, we have on the right side, we have the sort of the edge ML, we have Raspberry Pi and Jetson Nano, and those are the systems that we are exploring in this project that I just showed you. And of course, there are many more opportunities to take even to smaller systems, smaller device, which is on the left side here. We are still exploring the space. We haven't solved all the issues, but we can see opportunities in going to the left, especially when looking at the sort of power consumption aspect. And so this is the sort of space we are more on the right here space, and we're exploring the Jetson Nano, which is it's one of the NVIDIA, let's say, response to edge computing, in the sense that what you have, you can see on the left, you have the system there. You have you have a pretty decent GPU. It's a small scale, but it's a decent GPU, so you can do quite a lot of especially linear algebra intensive computations. So we can you explore the parallelism, for instance, adding numbers to matrix and things like that. But also, you also have a CPU, so you have a 4-core CPU on the system. But what is interesting about this design here is that traditionally, when you see GPUs, you mostly see GPUs, what is called discrete GPUs, where you have GPUs in your, let's say, in my desktop here. I put the GPU there in the PCI Express, and then that connects to the system. Of course, that has some memory implication, and the memory is the major bottleneck here for the system. So you have the GPU memory, you have your DRAM, your system memory, and then now you need to transfer data across. That's a big issue for traditional accelerated applications using traditional GPUs. So what you have here, very on the right side here, you have, just put the pointer here, you have this integrated memory, system memory, and this is something that it's helping a lot to improve the performance, because now the data is accessible by those two systems. So traditionally here, you would call a CPU as the host and GPU as the device, because GPU is, has been a sort of a graphics device, and it's sort of a, it is added to the bus of our computer. Okay, here you have this shared system memory. So what we look at this in this transition challenge, we look at the ways we can take these models that we train and put in devices like the cage, the inspection cage that I just showed you. Of course, those models, as you take those models, if you take those models, for instance, the TensorFlow, original TensorFlow model trained on the cloud, and we don't do anything with the model, it's going to have a kind of performance in running in this type of edge device. But if you do an optimization of the model, and some of the optimizations is on the right side here, you have model compression. So there are quite a lot of optimization you can do on the neural network architecture. And I also changed the quantization of the system. So using 16 bits for or 32 bits for the front float point numbers. So those are the techniques that we can use. So so what we have, the TensorFlow model originally trained on the cloud, and then we have the sort of optimized model, and that's using the NVIDIA TensorRT engine for doing those optimization. And then look at we look at the sort of aspects of those. So mostly looking at the process of loading models, so the initial process, loading package, initializing variables, then the sort of setup of the system, and also some of the first rounds we do for the inference, so that we fill caches and things like that, so that we have this warm-up rounds, and then we avoid this cold start problems where we start doing the inference, but the system is not yet prepared for the inference, and then we have quite a lot of overhead. This is also related to the issues that I think Colby mentioned this morning, which is the sort of a hidden depth of machine learning models. So this is the sort of cost, system level cost that we have in doing edge computing. And then we varied. So we had the original cloud-based model, and then we have two models, one using 16 bits floating point, the other one using 32 bits floating point models. Okay, so what you can see if you look at the power consumption, we can see that here at the top, we can see this is a MobileNet version 2. MobileNet it's now a standard architecture for this type of machine learning at the edge. So we can see that this model in the first part here, we can see that pretty much the model consumes okay for for loading libraries and warm-up rounds, but when we see the inference round, we can see an increase in the use of power in the system. So the top here is the original model, and at the bottom here we have the sort of optimized model at the bottom here, and then you can see also the different levels of the power consumption for those two. Okay, so but what is interesting is that when you look at the cloud-based model, which is the TensorFlow original model that we tested on the edge device, we can see that the accuracy, which was, it's always a question: do we lose accuracy? And then the answer is that for the data sets that we use, so remember, these are the images. This model is based on the images of the vehicle part that I mentioned. So we pretty much have we didn't see any difference in the accuracy of the models. Okay, but we saw quite a lot of improvement in the throughput. So this is frame per second. It's the sort of the image per second of the throughput that we can do, and then we can see that there is quite a lot of improvement when you do the optimization. So if you use, let's say, we change the quantization to 32 bits using so float point 32 bits, we can see that we go from 41 frames per second to 82. So it's kind of double the performance. Okay, but what is interesting is that the performance watt, which is this metric that connects power consumption and I know I'm going to finish, Marco. I know. So it connected power consumption and performance. We can see that for the let's say cloud-based model, which was tested and validated on the edge device, we have 12.10 frames per second per watt. But then we have 25.74 frames per second per watt and 26.01 frames per second per watt, which means that we have improved a lot in that kind of space. Okay, so so takeaway messages: so the Industry 5.0, human-centric, sustainable, and resilient. Automation versus human loop. So the transition from 4.0 to 5.0. So I showed an example of a quality control for automotive parts in the production cell. We managed to achieve 5 seconds. This is great for Industry 4.0. But then now we have a situation because that person, it's like lose the job. But what we can do, I mean, and then we are bringing this debug mode so that we can change the role and put the person in a sort of a high level in the sort of workspace. And the transition challenge is taking those models and put in the edge device. I was going to do a demo here, but we don't have time to show some of the, but we don't have time. So yeah, so yes, I can take some questions. I don't know if that.
Thank you very much, Marcelo. That was a great talk. So a round of applause on behalf of all the participants.